throughout the whole thing should, in theory, be the same.
Yeah,
So it doesn't matter which one I put first.
Well, it's just you said because you have the resistor or something, then the third graph is gonna look like the first one more than the second one.
Though, then potentially it's split there. I mean, there's gonna be a flavor of both. The fact that I have a resistor means it's not gonna build up it will not build up as fast as this one does. But the fact that I have a capacitor in there means that at some point that current's gonna drop off. The capacitor's not gonna fill up as quickly as it does here. And so it should drop off over a longer period of time. I'm trying to give some sort of sense that this is stretched out more than that is.
Can you represent that mathematically? Because that's like one of the ways that it said that you can do it is like, you put an equation next to it explaining.
Like to differentiate between two graphs if they're similar.
Yeah, like an x to the third or an x squared.
I was just looking for just a quick sketch there on these.
It says if there are two graphs that are similar, you need to differentiate them.
And you're going to do it mathematically as opposed to graphically.
Well, what's the differentiation in the graph?
Differentiation between these two graphs is the fact that it doesn't ramp up as quickly as that does. And my hope was that the decay takes longer than this one. This one has a steeper drop off here than this does.
Okay. Because of the resistor?
Yes. Because the capacitor is not filling up. Because here I start out with a huge amount of current to start with. Here, I'm not going to start out with a huge amount of current. I've got the limit on how much that current. Because if the capacitor were not there, it's going to look like this. So if those plates touched, this is what I'm looking at. But with the capacitor there, I know I'm not going to exceed this. So, and also with the capacitor, it's eventually going to stop the current flowing down that path as the capacitor fills up. Mathematically, I have an RC series DC circuit. So I have some voltage here. So I'm going to have delta V power supply minus the voltage across the capacitor minus the voltage across the resistor is equal to 0. If that's a positive plate, that's the positive and negative side, that's going to be the positive plate and negative plate. So as I go around the circuit here, I'm going from high to low, so negative. And a resistor, it's going to be negative. This is, so whatever my voltage of the power supply, I'm just going to represent that by EMF. Minus, that's Q over C, minus IR equals 0. This is the charge on the plates. This is the current going across the resistor. That mess. So as Q gets bigger, now as Q gets onto the plate, the rate at which Q gets onto the plate, the charge gets onto the plate matches the charge that comes off of this. So we really don't have to distinguish between the two. So I have some constant minus Q over C minus dQ R times dQ dt. Solve for Q. And then integrate, and you get the current. So if you want a math equation, so I have R dQ dt plus Q over C equals epsilon. first order differential. For equal to zero, it's simple, but not equal to zero,
Is epsilon not a constant?
is.
Wait,
And it's whatever the voltage the power supply is, so it would be a constant. C is a constant, R is a constant.
So why don't we just pull out all the constants and then integrate?
How are we going to?
Well, like,
Okay, yeah, no,
No?
so what you're suggesting,
Is it because it's equal to zero that's making it so we can't pull it out?
I mean, it sounded like you're suggesting, say, you get DQ all by itself and then everything else on the other side?
Well, with like having Q with DQ, yeah.
Yeah, how are you gonna get Q with DQ?
Algebra. I don't know. Can you not do
So
that?
if I did R dQ dt equals epsilon minus Q over C, and then,
Divide R over.
No. Multiply both sides by C and then divide
we still trying to get that Q over here.
Q. Yeah.
Oh,
But you can't.
there we go.
Right.
So I have DQ over. I'm gonna leave that there, so over epsilon minus Q over C equals 1 over R dt. There we go. I can integrate that.
Awesome.
So integrate both sides. Do a little U substitution here. U is equal to epsilon minus Q over C, so du is equal to negative 1 over C dq. So dq would be negative C du. So this over here becomes negative C du over U. Unless I've done a careless error somewhere. Equals one over R. So I have negative C natural log of U from whatever my limits are. My limits are from 0 to whatever Q sub m for max. Time is going to go from 0 to some time t.
Wait, why do we
What is
keep
this?
C?
What does the C stand for?
The capacitance.
Wait, so epsilon went to 0, Q stayed, but C doesn't.
Oh, yeah. So starts out, so this would be epsilon. And then we plug in whatever the maximum Q is, this would be epsilon minus Q max over C. Actually, generically, Q.
If we get a question like this on the test, can we stick to the graphs?
Yeah,
Okay.
yeah, this was just because there was a request for the math,
Well,
so.
you're
I
gonna
didn't
see
know.
on the right side, right, and then you're gonna end up with some sort of logarithmic
Yeah.
function on the left, which makes sense because that looks like a logarithmic graph.
So you end up, and this is as it charges. No, should be as it charges. Q, so it's negative C, natural log, epsilon minus Q over C divided by epsilon is equal to T over R. Bringing C over, so I have natural log of this is equal to negative T over CR.
Where did you get the epsilon minus QC over epsilon?
We plug that in for U, minus plugging that in for U. And the natural log of A minus the natural log of B is.
Oh, I see.
A over B. That, see that property? So I have epsilon minus Q over C over epsilon equals e to the negative T over RC. Solve for Q.
Actually, that's one of our equations.
Yeah, it should be. Once you have Q, you can find the current by taking the derivative with respect to time.
Time constant is RC.
Yeah.
Yeah. And that's kind of cool, just to write
I don't know what my mental block is. When I see first order differential equation that's not set equal to zero, my mind starts going into not calc, but diffie Q.
Yeah.
And I'm going, diffie Q. I remember doing it.
Well, you have so many letters there, because if you had another variable and those weren't constants, then you would have whatever it is where you can't differentiate it easily because it's like non-linear or whatever, it's like, because you can't separate the variables. in order to differentiate it. But those are all constants, so that's why it worked.
Yeah,
But it looks like it wouldn't work because of all the letters, I think, is probably.
childhood scars. Dave?
Yeah.
Oh, sorry, I didn't do the last one yet. Is that?
No, what is the formula of 1/2 pi epsilon sub naught times lambda over r?
Whatever the 2 pi.
It's in the electrostatics, you know.
Isn't that like something with parallel plates?
1/2
Even
pi
like
epsilon
charge.
sub naught lambda over r. It's the bottom one. of the questions.
If it's 4, then it's,
Tell me there,
so
1/4 pi Q.
Oh,
Oh,
or something.
that is the,
Specific.
sorry, that one.
Yeah, that's all.
That is the electric field coming from an infinite line of charge with a distance r from the line with a linear charge density of lambda.
Charge on the.
4
so
pi
charge on the line
is not in
from
front.
the distance, from the distance of what?
Your distance r, so you have a line of charge and your distance r away.
Oh,
That's the magnitude of the electric field.
Okay.
Can you finish this one?
All right, so over here, I have current that's, once I make the connection, I have current that's gonna flow down here and flow down there. I believe the question was the current going out of the power supply, so this is
Yeah.
the first place where it's not flowing across.
Which
everything.
brings up more questions in my mind, because I don't really know where you're measuring, like, the graphs from, like the
Yeah.
current.
Technically, I would put the ammeter right after the power supply.
Okay, then you had it going into the capacitor first, then the resistor, right?
It's, would be flowing in that path and that path
I
simultaneously.
know, like the other graphs, but,
Oh.
yeah, the third graph, sorry.
The order in which they're drawn would not change. The only thing that would, if I flip those around, that would change is those two would flip positions, but they're still subtracting both of them.
Why doesn't it affect the graph though, if you're having a capacitor charge before it hits the resistor? Because if it's flowing out of the positive terminal.
When I have a wire, typically a wire doesn't have any holes. I mean, there's no place for the electrons to go. In other words, the wire's neutral. In order for charge to flow out, as soon as you connect it, basically you have an electron jumping into here, then creating a hole, and then an electron moves, and we get electrons sort of chain reaction.
Oh, it's because the electrons are moving the other way, like from the negative direction. It's like you have the current going from the positive, but then the electrons are technically going from the negative, so it kind of evens out or whatever. So
I wouldn't have gone that far. No.
No.
It's the fact that we have current flowing out of here and into here, that basically a hole needs to be created, and so they're dependent upon each other. So I need an electron to come into here in order for an electron to come out of here. All the electrons would shift. And so the rate at which electrons would flow has to match the rate, at this point, has to match the rate at which electrons are flowing at this point. Unless you want to get down to a nanosecond, which I don't.
So you should be like thinking of it as looking at the whole circuit, the whole rest of the circuit from the battery, not like one direction from the battery, I guess.
If I understood that, yes.
Yeah.
Now, in the last case, we're gonna have parallel. I basically have, I can think of it as two circuits. I've got that right there, which we plotted here. We have that right there, which we plotted there. Because current's gonna be flowing down either path, it's just gonna be the sum of those two.
Which is,
So the last one is just, should look taller. It will, eventually the capacitor will fill and this part will get blocked off. And so it's gonna look kind of like that, except it's going to it should basically bottom out at whatever level that is. That is really poorly done.
looks like an ocean wave.
That's what I was going for, okay.
Why doesn't that go to 0?
Because even after the capacitor fills up here, I still have this path. Here, the capacitor fills up and it blocks flow. Here, the capacitor fills up and it blocks flow along that wire.
Okay. Really quick, if you were to do voltage versus time, how would the graphs look different? Or is that too long of a thing?
Well, for these, if we're talking the voltage of the power supply, that would be, I guess it's not connected, no, the voltage of the power supply.
It's always the same. Yeah. I've seen voltage versus time graphs though where it changes.
And we could do voltage across the resistor,
Okay.
or voltage across the capacitor, but if you're going voltage of the power supply, then
Yeah.
ideally, the voltage of the power supply is the voltage of the power supply, whether it's connected or not.
Are you gonna ask us about voltage and time over a resistor, like graphing?
I hadn't considered it, but
Okay.
now that I would have said that.
Well, now that I've said maybe you should go through it then, like if you're considering.
I know that the voltage, well, the resistor is simple, because V equals IR, resistance is a constant, and so my voltage graph's gonna go a whole lot like that, except, if voltage is bigger than 1, the graph will be up here, less than 1 down here, or on a different scale, it's gonna look like that. For a capacitor, I know that the voltage across the capacitor is Q over C. Because going back to capacitance is defined as Q over delta V, and so just solve for delta V. I know that the current is dQ dt. So if I'm linking it back to the current, I know that delta V, C delta V is equal to Q. So dQ dt would be C times dV dt. That's my current. So my voltage with respect to time is going to be I over C. And so I varies like that. So my slope of my voltage graph should basically be looking something like that. Because that's I divided by some constant.
It's like scaled by the 1 over C.
Yes. So that is the slope of my voltage versus time graph. So across the capacitor. I don't think there's a minus sign in this there. So if I've got, so that is a slope that starts at 0. this is my, so this is my slope, and a slope that starts at 0 and gets bigger. I'll think about where 0 is in just a moment.
Well, it's 1 over C.
It gets bigger,
So the
and
run-
then it drops off. And then the voltage across the capacitor as it fills up should drop off.
Yeah, like stretches it out. Cause if it's rise over run, 1 over C, C is gonna get bigger, so the run is gonna get bigger, so it's gonna stretch it out. Right?
I think so. I'd have to think longer about that.
1 over C is the slope, right?
No,
No?
I over C is the slope of my voltage.
Oh, the whole thing is the slope.
Yeah.
What's the?
Well, this is I versus T. If I did 1 over C, that would scale this either up or down. And then, but the shape is basically the same. If the shape's basically the same, that's why I was just using this graph, ignoring the C. And trying to figure out what graph would produce this slope. The slope of what graph would produce this. So, if I start out with a slope of 0, my slope gets steeper as I go. Then there's going to be some sort of peak. My slope, no, that's right, it's positive the whole time. Oh, it's positive the whole time. So I'm going to start low, I'm going to move up to a certain point. I is positive the whole time, but gets closer and closer to 0, so this actually would, I think, level off. So the slope gets steeper and steeper and steeper up to a maximum peak. And then the slope of my V term, gets smaller and smaller and smaller, but still positive. And so, yeah, that's more like it.
So that's the voltage over time across the capacitor.
Yeah. And you're at maximum voltage when you're at maximum charge.